Okay, so what we have to prove is this. We have to prove that probability of A given B plus probability of A complement given B complement equals 1. So I break up these two terms and deal with them separately. So first let's see probability of A given B. So by the law of conditional probability, this is equal to probability of A intersection B divided by probability of B. And because we know that A and B are independent, we can rewrite this as probability of A into probability of B divided by probability of B. And this just cancels out to become probability of A. Now, as regarding the other term, let's assume that if A and B are independent, then A complement and B complement are also independent. This is not entirely intuitive, and I will do the proof of this later on. But for now, just assume it to be true. So we can rewrite probability of A complement given B complement as probability of A complement intersection B complement divided by probability of B complement. And then using the same principle as above, we use the independence property to rewrite this as probability of A complement into probability of B complement divided by probability of B complement. And this just becomes probability of A complement. So now when we add up these two terms, this becomes probability of A plus probability of A complement, which is equal to the probability of the certain set S, which is always equal to 1. So we have proved that the statement is true. However, our proof rested on the crucial property that if A and B are independent, then A complement and B complement are also independent. So now let's prove this. So to prove this, I multiply probability of A complement with probability of B complement. And if I can prove that this is equal to probability of A complement intersection B complement, then this means that A complement and B complement are also independent. So probability of A complement I rewrite as 1 minus probability of A, and I can rewrite probability of B complement as 1 minus probability of B. So then expanding this becomes 1 minus probability of A minus probability of B plus probability of A into probability of B. And this term here, because A and B are independent, I can rewrite this as probability of A intersection B. Then I take the negative sign common, and then I group these three terms. And what are these three terms? These are probability of A plus probability of B minus probability of A intersection B. And this is none other than probability of A union B. So then our equation becomes 1 minus probability of A union B. Essentially what this means is that you combine the set A with the set B, and then you subtract it from the certain set S. So this means that you can have neither you don't have neither elements of S nor elements of B, but you have everything else. So that means this is equal to probability of A complement intersection B complement. That is, this set contains all those elements which are neither in A nor in B. So hence we have proved that A complement and B complement are also independent, and given this property we can easily prove the given statement.